Chapter 5 deals with circular motion and universal gravitation. Now, circular motion is a pretty neat thing, actually, you know. And somehow the circular motion and universal gravitation can be combined together to have planetary motion. We can explain how planets move around the sun and other satellite motion, such as moon or artificial satellite, can orbit around a planet, right? And circular motion is a class of periodic motion, so it just completely repeats itself, right? It's a motion that repeats itself, that completes a cycle, that finishes where it starts, that oscillates. Motion that repeats itself, that completes a cycle, that finishes where it starts, that oscillates. Motion that repeats itself. I hope you get the point, right? So it just goes, circle around and round and round. It just continuously repeats, right? So if you go back to, I guess, trigonometry or math analysis, right? If you were to think about like unit circle, right, and circle with arc length and radius and so on, right, we have to understand some mathy stuff in order to do some circular motion. So if we had a part of a circle, right, now circles are much, the whole circumference here and the radius, but if we took a part of that circle, that part of that circumference is called the arc length, okay? Arc length is a part of a circumference. Now, radius is a distance from the center of the circle to the circumference or the arc length itself. And radius is constant, and so it doesn't change as it goes around a circular path. So when the Greeks actually decide to analyze the circle, these are ancient Greeks, by the way, right? When they actually measure the circumference of any circle, no matter how big or small the size of the circle was, right? When they get a piece of string, and then they would actually measure the circumference, right? And then they would open this string up and then find out exactly how long that string was, right? And then they get the measurement of the radius of that circle, right? And then when they divided the circumference of that circle, divide that by the radius of the circle, they always got this strange ratio no matter what size the circle was. And that happened to be like 6.283, blah, 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 right? And they call that constant tau, right? Tau. Well, they decide to break that tau up into 2 pi, and that's how we got the 2 pi, right? So the circumference, right, divide by the radius is equal to tau. And that tau is the same as 2 pi. Now, circumference is measured in, let's say in our modern time, the unit for circumference is a length, so it's measured in meters. And radius is also unit of meters because it's length. So if you think about it, this tau or this 2 pi should not have any units at all. It should be just a pure number. It should be a ratio of a pure number. But they decide to give this fictitious unit called radians. So this unit, radians, is kind of magical, right? It could appear anywhere, or it could just poof, disappear, and you can't really do anything about it. Because this radians itself is just a figure of just fictitious unit representing a ratio of circumference divided by radius. Okay? Well, if you don't have a circumference, but you only have a, let's say, fraction of a circumference, they have this thing called arc length. Now, arc length divided by radius They call that theta. And this theta is measured in radians. Okay? In a complete circle, we have 2 pi radians in a complete circle. Okay? So ratio of arc length over radius. So that's what theta means. The unit for theta, again, is in radians. Now, we should be able to convert radians to degrees, right? Now, when a complete circle happens, they decide to divide that one large circle into 360 equal parts, and each of those equal parts, they call it degrees, right? So 2 pi radians has same value as 360 degrees. Okay? Well, this is kind of ancient now, but I would like to actually introduce you to my methodology, and I like to call this metric circle. And in one complete circle, there should be 100 kims. Again, this is not real, right? But I think it should be. We should start like a whole trend in, like, change.org saying metric circle, right? 100 kims in one complete circle, right? I don't know. I don't know if it'll catch up. All right. Well, this is not yet realized. However, this definitely is. Okay. So if we divide both side by 2, then pi radians is equal to 180 degrees. Okay. So if you ever want to go from degrees to radians, all you have to do is multiply the factor of, right, pi radians over 180 degrees, and then you multiply the degrees by pi and divide by 180. So 75 degrees is equal to 1.31 radians. Okay? Now, conversely, if you want to go from radians to degrees, all you have to do is multiply the radians by 180 degrees, divide by pi radians, right? And you'll get yourself degrees. So for example, 3 radians, if you multiply that by, right, 180 divided by pi radians, and pi definitely has a value of 3.1415, blah, 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 blah. Okay? Therefore, you have 172 degrees. All right, so hopefully you can do the conversion. All right. Uniform circular motion. When you talk about uniform circular motion, uniform means constant speed. Okay? It's going in a circle at a constant speed. Okay? Circular motion, right, means the direction is changing all the time, right? So uniform means constant speed. Circular motion means the direction is always changing. Okay? Direction is always changing because it's going this way and then this way and then this way and then this way and this way. So direction is always changing as it goes around the circle. Okay? So, can an object moving with a constant speed have acceleration? Well, the answer is, since the direction is changing, so for example, here, and then at this location, here, and then at this location, here, and at this location, here, the direction is always changing. Therefore, if the direction changes, then your velocity changes, because your velocity has magnitude and direction. Well, if you're going at a constant speed, your magnitude doesn't change. If you're going faster and faster, then your magnitude changes. Well, when magnitude changes, you have change in velocity. But what if you're going at a constant speed? Well, then your magnitude doesn't change. However, your direction changes. When your direction changes, then your velocity changes because it's a vector, right? So when there is change in velocity, there's no negotiation. There has to be an acceleration, right? So although the speed, which is the magnitude of the velocity, does not change, right? The direction, however, always changes. Therefore, there is a change in velocity. And this is the most important part. If there is change in velocity, there must be acceleration. No negotiation on that, right? There's no negotiation on that whatsoever. So even though it's going at a constant speed, if the direction changes, right, then we have change in velocity. If there is change in velocity, then there must be acceleration. All right. Well, how are we going to find this acceleration then, right? We need to look at some objects going in a circle, okay? So this is very important. Any questions? Okay. So here we go. Let's understand some few items here. We have to understand some terminologies and definitions of what period is. Period represents the time to complete one revolution or one complete cycle, right? And is represented with capital T. Okay, so And it is measured in seconds. Okay, seconds. Or sometimes it is represented as seconds per revolution. Oops, not rev. Seconds per revolution. Okay. Frequency represents how often, you're not supposed to pronounce the T, right? But how often, right, it completes a cycle or revolution, right? In 1 second. So it is pretty much represented as revolutions it completes in 1 second. So revolutions per second. Okay? Or otherwise, just 1/2 second. And this can also be represented as hertz. All right? So, how are period and frequency related? Well, it seems like the period is equal to 1/frequency, or the frequency itself is same as 1/period. They're inversely related to one another. Okay? So these are some definitions that you should definitely remember. Okay? All right. So how do we find the speed of an object going in a circle? Well, if you see something going in a circle, how do you find how fast that thing is going? Well, I would basically find out how much time it takes to make one complete revolution, right? But it's really hard to do that when it's going too fast. So what do? You count like 10 revolutions and basically time how much it takes to go 10 complete revolutions. And then if you divide that time by 10, you get yourself the period, right? Number of seconds for one revolution. Right? So here, if you were to take a look, right, let's say we know an object makes 10 revolutions in 2 seconds. Right? So with that information given, find the frequency. Right? Well, if we makes 10 revolutions in 2 seconds, my frequency would be 5 revolutions per second. However, with that same information, if I want to know what is the period of that object going in a circular motion, it's simply 2 seconds divided by 10 revolutions, or simply 1/5 of a second, or 0.2 seconds per revolution. Okay? So I hope that's easy enough. Okay. Now, once we know how to calculate the time to make one revolution, if we could find the distance that it travels in one revolution, then we can find speed. So how far does an object move in one revolution? It basically moves one complete circumference of it. That's the distance, right? That's the distance. So one revolution has 2 pi times the radius worth of circumference. That circumference is the distance traveled in one complete revolution. So now we have all the ingredients to figure out how to calculate speed. Speed is distance divided by time. Distance is calculated as 2 pi r. The time it completes that one revolution of 2 pi r is called period t. So the speed of the object can be calculated as 2 pi r divided by the period t, or simply 2 pi r f, which is the frequency. So these are the ways to figure out the speed. All right? All right. So let me see if you can calculate this. Okay, humor me. So please calculate the period and frequency of Earth as it travels around the sun. Now don't forget, the period should be measured in seconds. Okay? Period should be measured in seconds. And frequency should be measured in hertz. So I'm going to pause the video for about 5 minutes, and let me see if you guys can figure this out. And if you're done with this, move on to example 2. So right now it's 10:01, so I'll meet you back here at 10:05. All right? All right, so here we go. Let's take a look. Now we all know how long it takes to make one complete revolution around the sun, right? So if we have the sun right here, right? Sun, sun, Mr. Golden Sun, please shine down on me. Mr. Sun, sun, Mr. Golden Sun, hiding behind that tree. So here's Mr. Sun, right? And here's our planet Earth, which is, here's the Earth, right? With a little speck of green, right? Because we do still have some green stuff and lots of forest fires. You know. It's going around, right? It's going around the sun. And we know it's going to take 365 days to go around one complete revolution. So the period of the sun is 365. I know somebody's going to say, Mr. Kim, technically, it's actually 365.25 days because it's a leap year. Right? Fine, be that way, right? I could see that in my, my AP class. So, Mr. Kim, you forgot that corner day. All right, so now we know it's 365.25 days. And in one day, there are 24 hours, right? And in 1 hour, there are 60 minutes or 3,600 seconds, right? And 1 minute, there are 60 seconds. So, if you do your math correctly, this is the period of Earth going around the sun. This 31,557,600 600 seconds. So that's the period of the Earth around the sun. Right? You could say seconds per revolution if you want to. Okay. So there's 365 days per revolution if you want to. Okay. So that is the period of the Earth. Well, what about the frequency then? Well, the frequency. Oh, did I switch the colors? Oh, sorry. Oh boy. Sorry. Okay. All right, so the frequency is basically 1 over the period. So this one's easier to calculate because it's just 1 over the period that we just calculated, which is 31,557,600 seconds per revolution. Therefore, this revolution will go on top, right? And that comes out to 3.1688 times 10 to the negative 8th revolutions per second. Right? So it only completed this much turn in 1 second is what they're saying. Or simply 3.1688 times 10 to the negative 8th hertz. Okay? All right. Here, let's say, we know an object makes 20 revolutions in 4 seconds. Calculate the period and frequency of the object. In this case, it's probably easier to figure out the frequency first, because frequency is how many revolutions in seconds it is, right? So there are 20 revolutions in 4 seconds. Okay? Therefore, this is 5 revolutions per second, or simply 5 hertz. Okay. Well, to figure out the period of that, it is 1 over frequency, and that is just 1 over 5 revolutions per second, or simply 0.2 seconds per revolution. Okay? Is that good? Is that good enough? Alrighty then. Now comes a little bit of tedious stuff. Okay? Now we know how to calculate the speed. And we know the direction constantly changes. So we figured out that there has to be non-negotiable acceleration. Well, how do we calculate the magnitude of that acceleration, right? How much is my acceleration numerically? To do that, I'm going to prove to you just once. And you don't have to learn how to prove this every time you use it. Once we prove it together, just use the formula that we proved together. Okay? So here we go. All right? So by definition, okay, an angle between the radius and instantaneous velocity is always 90 degrees. So what does that mean? When things are going in a circle, right, the direction of the velocity is tangential velocity, which means it is going off in tangent, right? So as this object is going around in a circle, since this velocity is tangent to the circle, And if this is tangent to the circle, then this is perpendicular to the radius. So the angle between the velocity and the radius is 90 degrees all the time. Okay? And that's good to know. That's good to know. Right? So if I were, let's say this is like going in a circle on a table, let's say. We're looking at it from bird's eye view, right? If I were to turn this thing around, round, round, and then let go of the string, this object, when I cut the string off right here, will fly off straight in a tangent to its circular path. Okay? Straight out tangentially. Okay? Same here. If I let go of this right at this moment, this thing will fly off straight out tangentially. Okay? So even though the speed is the same, so notice the magnitude of my velocity vector is same length, the direction is completely different. Okay? So for this to remain true, the angle between R1 and R2 must be equal to the angle between V1 and V2. So if I were to look at this velocity here and this velocity here at two different times, right? Since this is 90 and this is 90, right? This angle right here that this R sweeps out from A to B has to be same angle between, if I were to place this at the tip of my, a tail of my A, right? This angle and this angle are the exact same angles. So by using, right, a similar triangles, so for this one, right, R, R, right, 1 and R2, and this arc length right here, right, and this angle theta. And if I were to look at this, right, which is V1, I'm going to draw it, I'm going to draw this like rotate it here, okay? So V1 and V2 right? This angle is also same as that angle. This is exactly same as V2 minus V1. So this is my delta V. Okay? Or if I were to do V1 and then V2, right? If I bring the V2 here, let's say, straight down, and then subtract my V1. So here, let's say, like 1 point, a little more than a hair, right? So 1 point, a little more than a hair. So here's my, let's say, negative, right? Yeah, crap, sorry. Here, yeah. Here's my negative V1. Then this is my delta V. So R stays the same. The length of my V1 and length of my V2 are the same because it's a constant speed, right? And since these are similar triangles, this distance right here across, which is actually L, is exactly same, well, not exactly, but very close to this arc length S when the angle is less than 10 degrees. Okay, now here we go. So delta V over V has to be same as L, right? So delta L, this is from here to here, over R, because it's similar triangles. Proportionality, right? So if I solve for delta V by multiplying both sides by my V, I get delta V is equal to V over R delta L. If I divide now both sides by delta T, right? Then notice, this becomes my acceleration. This delta L over delta T, delta L is similar to arc length S if theta is less than 12 degrees. So I can replace this delta L with S. Then what do I have? I have my acceleration is equal to then V over R times S over delta T. Well, what's S over delta T? That's my V. This is my V. So what do I have? I have acceleration now is equal to V times V over R, or simply V squared over R is my acceleration. So this acceleration has a magnitude of V squared over R. Now that we proved it, you don't have to keep proving this to use it. I just don't like to throw up an equation and say, oh, memorize this. Some students have an idea like, wait, where did that come from? How did that come from? Well, here it is. This is how it came. So now we have a new definition of acceleration. However, this acceleration is circular acceleration. So I'm going to put a sub c down to distinguish this from my other acceleration that we learned earlier, okay, which is the linear acceleration. So a sub c, or circular acceleration, is equal to v squared divided by r. This is very important. All right? So you can see my v squared, this will always be positive, right? It's a speed squared. My radius can never be negative. So my acceleration in the circular motion will always be positive value. Okay? So the magnitude of the acceleration can be found by v squared divided by r. Well, we know acceleration is a vector. So we know the magnitude of my acceleration. So this is just the magnitude. But what about direction? Well, let's find out. Okay. The direction of my circular acceleration, okay, is going to have to be found by some logic. Let's say we see an object going in a circle very, very, very fast, and we pick out two times close to each other, right? T1 and T2. So we call them initial and final. Now, these two time frames are very small, okay, because it's going in very, very fast. The velocity at T initial will have tangential velocity VI, V initial, which is 90 degrees to my radius R, right? And similarly, my final velocity at T final will also be tangential to my circular path. So this is also 90 degrees. Okay? Now, if I were to place this final velocity at this middle area between the two time frames. So here, watch this. So here I'm going to calculate, here's my final velocity. I'm going to make it a little more than an inch, it looks like, right? So I'm going to actually draw my final velocity, exact same direction, same magnitude, slightly more than an inch, right? So here's my VF. I will do negative VI, right? Because what's my delta F, and then my delta V is equal to basically VF minus, right? Well, I'm going to say plus negative VI, right? Right? So if I add negative VI to my VF, what's it going to be? Well, it's going to be simply, again, slightly more than an inch, right? Going this direction, and it has to be parallel with this. Notice I am doing parallel, parallel. I'm going to start from the tip, add my negative VI onto my VF. So here's my delta V. Here's my delta V. So, since my acceleration is equal to delta V over delta t, my acceleration will have exact same direction as my delta V direction, right? Therefore, my centripetal acceleration, or the circular acceleration, will have exact same direction as my delta V direction, which is in towards the center of the circle. So Therefore, because it is pointing towards the center of the circle, my acceleration is always seeking towards the center. So, is it centripetal or centrifugal? Now, centri, from Latin centrum, right? The middle point of a circle or the center. Petal, from the Latin peto, to seek, to strive after, endeavor to obtain, right? Or fugal means, Latin means fugito, to flee, to fly from, avoid, or shun. So since my acceleration is seeking towards the center, right, it has to be centripetal acceleration. So this acceleration is center seeking. Therefore, it is centripetal acceleration. Now we have both magnitude and direction for circular acceleration. Okay? So for A sub c, right, we have v squared over r, comma. The direction is towards the center. This is my circular acceleration, or otherwise known as the centripetal acceleration. Whew. All right. That was very important thing that we did. Okay? So now we are ready to do some serious circular motion physics. Now this basically is exactly what I just did. Instead of just showing this, I actually drew it out so you guys can follow through, right? So this is just exact same thing that I did here, okay? Already, like so. Okay? So to figure out the magnitude of my acceleration, centripetal, I need to know the speed of the object and the radius of the object. Okay? Centripetal acceleration can also be represented as radial acceleration because it is along the radius. Okay? So make sure you know as both terminologies, centripetal acceleration or radial acceleration. All right. Now that we did that, I will give you a little break and see if you guys can answer the next 2 pages on your own for the rest of the period. All right. And then, I guess Thursday I will meet with you, and then we will do some other acceleration equations, which is Yeah, I'm not gonna go too nuts. And then I'll let you do the finish up the rest of the homework on Thursday. And then that would be pretty much what the plan's gonna be for Thursday. All right. So for today, I'm finished with the lecture. Okay. I'll go over this. Okay. On Thursday, and then we'll start the non-uniform circular motion. And after we go over non-uniform circular motion, I will let you do some homework problems on Thursday. All right? So for today, let's work on this for the rest of the period. And this. This is pretty easy. So you should be able to get these done. All right. Any questions? All right. I'll stop the lecture here.